So again, we have 5 more fantastic speakers. So I'd first like to invite Josh Bongard, if he would like to present his work, please. Hi, Josh.
Hi there, Josie. How are you?
Very good, thank you. Great to have you with us today. Thank you.
Thanks for having me. Okay, so as promised, a short talk on what I believe non-embodied AI is missing. So Catherine was just walking us through the human scale. If we dive down to the micro scale, we learn that the short answer to what non-embodied AI is missing is it's missing a lot. Microorganisms, single-celled organisms, like the one that you see here, they have been exhibiting intelligent behavior for billions of years without the benefit of a nervous system. So the history of AI and robotics is obviously one of bioinspiration. There is much in biology that we have overlooked in our emphasis on brain or neuro-driven behavior. So in some recent work in embodied AI, my group has teamed up with the Levin Lab, and specifically Mike Levin and Doug Blackiston at Tufts University. And we recently reported a series of papers on what have now popularly become known as xenobots. These are also aneural organisms. The xenobot that you see in the bottom half of this video is walking along the bottom of its petri dish without the benefit of any nervous system whatsoever. What you're seeing in the top half of this video is the original design for this xenobot that was dreamed up by an AI. In this short talk, I don't have time to go into how the AI actually goes about designing xenobots. I will just tell you, if you don't know already, xenobots are about 1 millimeter across. You might just be able to see the xenobot in the plate here being held by Sam. It's about 1 millimeter across. It's built completely from genetically unmodified frog cells, and as I mentioned, there is no nervous system here whatsoever. So I think as synthetic biology and AI start to combine, it's going to take us in lots of different directions for looking for inspiration about intelligent behavior, and specifically into aspects of biology that we may have overlooked in more traditional approaches to AI that tend to be focused on nervous systems, and in particular on human nervous systems. We published the first Xenobots paper back in January 2020, where we showed that we could get an AI to design living robots that walk. At the beginning of 2021, we showed AI-designed Xenobots that are able to swim. You'll see in a moment here a swimming Xenobot, again, a millimeter across. This particular Xenobot is swimming using small cilia. These are very small, flexible hairs that grow on the surface of frog skin cells, the material from which xenobots are built. And you can get, for example, swimming behavior, again, without the benefit of a nervous system. This past December, we published our third paper in our series on xenobots. And what you're watching here, obviously sped up, is a swarm of xenobots. They are pushing individual frog skin cells in the dish into piles. And you'll notice this pile in the lower left is becoming relatively large. Turns out that if there is a large enough pile of self-adhering frog skin cells, they will grow these small cilia, these small hairs. And after about a day, that pile that you see in the bottom left will grow these hairs, and it will start moving on its own. And you have a quote unquote child xenobot. It's a form of replication, not biological reproduction. It's a form of replication that's been dreamed up. It's been thought of for a long time. John von Neumann back in the 1960s talked about robots building copies of themselves. What you're watching here is a living robot making a copy of itself. Whether or not you would consider this intelligent behavior, whether or not the xenobots here know what they're doing, these are questions that we don't have answers to at the moment. I just wanted to share some of this recent work with you as inspiration inspiration about broadening our view of how intelligent behavior is possible, and how we can take inspiration from these biological behaviors to think differently about building intelligence into machines. The other interesting thing to me about the Xenobots project is, again, it suggests there are these brand new kinds of materials that we can build robots from. Exotic materials, or thinking about materials, has been an important part of embodied AI for many decades now. There are many people working with very interesting exotic non-biological materials. Here we see robots built from biological materials. I've got just a couple minutes left, so I want to actually talk about inorganic materials for a moment. I'm going to talk about some recent work now that is not about the Xenobots. It's again looking at materials and trying to take inspiration from other places. This is taking inspiration from the field of materials science, and in particular, metamaterials. Metamaterials are artificially designed materials that are made up of very small parts of traditional materials like metals, plastics, and ceramics. What you're looking at here is a granular metamaterial. It's pretty straightforward. It's basically just some flexible particles, in this case placed into one-dimensional configurations. If you then supply a constant frequency at the left side of these materials, you get interesting vibrational properties. You'll see that some of the inner particles are vibrating at larger amplitude than they do on the left. In some places, vibration is snuffed. In some places, it's magnified. So we can seek inspiration in the inorganic world as well. And then we can design these materials to exhibit increasingly intelligent behavior. Here's a simulated two-dimensional granular material. The dark gray circles here are stiff particles. The light gray circles are soft particles. It turns out that this particular material, if you choose two particles and you supply zeros and ones as no vibration or vibration, you can actually get this material to act as an AND gate. You can detect a vibration appearing at a third distant particle only when the two input particles are vibrated. You can then wrap this in a search process. You can wrap this in an evolutionary algorithm that will search over the space of all possible materials, seeking those materials that exhibit this particular computation better. They have increasing AND-ness. You can expand this to a multi-objective optimization exercise, where now we are still searching over the space of all possible materials, but we're looking for materials that act like an AND gate at low frequency and act as an XOR gate at high frequency. Here's a different material that these evolutionary algorithm found that operates as an XOR gate at high frequency. Very surprisingly to us, we found a third material, we actually found a series of materials, that if you combine input frequencies, you can get that material to act as an AND gate and an XOR gate at the same time, at the same place, without recourse to quantum effects. So this is computational superposition. It's a very kind of surprising property. Again, whether you would consider this intelligent behavior or not, we can argue about that fact. Again, this is just meant to be a reminder that there's a lot out there in the organic world and the inorganic world that could provide stepping stones towards intelligent behavior in machines, either living machines or artificial machines, that we often miss or we overlook when we focus on deep learning, neural networks, V1, the usual suspects that are the focus of attention in traditional AI. I will stop there. Thanks very much, and I look forward to the panel discussion.
Thank you so much, Josh. Really, really amazing work to see. Just one quick question. You present both a very biological-driven approach and also an inorganic solution to creating some quote-unquote intelligent systems that maybe can perform some decision-making. Do you think these two come together, or do you think do they exist in separate, or should we try and bring them together?
Great question. So this is very recent work. We showed this metamaterials work to our colleague Mike Levin, who's a biologist. And we said, are cells doing this? Are they doing computational superposition? Are they computing different functions in the same place at the same time? Mike's response was, Absolutely. It's unlikely that biology would not make use of this particular phenomenon. It was relatively easy for us to evolve an inorganic material to do it.
Yeah.
It'd be unlikely that Mother Nature didn't also, discover this long, long before we did. We don't have a specific example of that yet at the cellular level, but I'm pretty sure we're going to find it pretty soon.
Really, really fascinating stuff.